All right, good to go.
Cool. Might kill himself on that cord. All right, let's start off. We're going to start off with kind of a basic general process that we're going to use for another process. But first thing I just want to talk about is this idea of a series that depends on a variable. So that's what power series are. These are just series that depend on some variable, and that variable is invariably going to be x for us. Just some real number x. And the value of the series will change as x changes. It may or may not converge for all x. So a power series in general looks like this. We've got a sum, they usually start at 0. I've got these constants. So these are constant coefficients. And so right now, this basically looks like every series we've ever done. It's just a sum of numbers. But what we're going to do is multiply each one by this x minus c to the nth power. So this is going to make it start looking like a polynomial in x. And when I write this out, as we always want to, this is going to be a0 times this thing to the 0 power, which is what? What's this to the 0 power? 1, perfect. And then when I go, thank you, so when n equals 1, I've got a1 times x minus c to the first, plus a2 x minus c squared on down the way, and that just keeps on rolling. So it looks a lot like an infinite polynomial, and I guess it is. The c is called the center of the expansion of the power series. And this is the basics. So the first question I just want to talk about is, if I gave you this, first off, notice that the value will change as x changes. So for example, what is the value? If I think of this thing as a function of x, which is what we're going to want to do, that's what today is actually all about. Having a function that looks like an infinite polynomial. What is f of c? Say that again?
Like the same sound, but depending on C.
No, so look, the c is still in there. You're going to replace the c with x. So what happens when you replace the x with a c?
What do we get? Cancels out.
Cancels out, and what am I left with?
1.
So this goes to 0. 0, what I have?
It's
Just a0. So notice that this series, any power series, it converges at its center. So at its center, it's just that first constant term, if there is one there. So every power series converges at its center.
Yes, right, and that's why it's 0.
Let me stop. So does that make sense? Do you see where I'm coming with that? Yeah, okay. Cool. I can't answer that question about any other value of x, because I don't know what a1, a0, and all those coefficients are. But what we're going to do first is we're going to get a general process so we can figure out what values of x do work in this thing. And we're going to think about a thing called the interval of convergence. So the interval of convergence is going to be some part of the real number line. So this is the real numbers. And we know that c is always a part of it. And what we're going to do is figure out how far away from c can I move and have those values have the values of x. So these are the x values. How far away can I move and still have the series converge at all these values inside here. So what we're gonna come up with is a distance r, and the series will converge if I move r units to the right or r units to the left, not including the endpoints necessarily. So what we're gonna come up with is some interval like this, like 0 to 2. And our series will converge whenever x is between 0 and 2. The interval is always symmetric about the center. So what would be the center here? Just looking at this interval. 1, yeah. And the radius r would be 1, just looking at that. So the center is always just right in the middle of that interval, and the radius is the distance to the left and the right, and they're always the same. Questions? Yes, Jose?
No,
Oh, you're doing the computation, you're doing it, okay. Is it working for you? Awesome. So, how to find r? Step 1. We're essentially going to use the ratio test. So it all falls back on the ratio test, which we already talked about, but let's see what it looks like here. I'm going to call this whole thing u sub n because it's a combo of these numbers and then the variable part. So think of u sub n as just this term. So this is u1, this is u2, this is u0, u1, u2. So use the ratio test, and we're going to set r, and so this is going to actually be r inverse here that I'm going to come up with, and it'll all make sense in just a little bit. This is going to equal the limit as n goes to infinity of the n plus first term times 1 over the nth term. So this looks like the ratio test here, hopefully. Yes, sir?
What's u?
U is this product of a sub n times x minus c to the n. So this is u0, this is u1.
Okay.
This is, I'm just trying to grab them all together. Okay, cool. Connection, rock and roll. So we're gonna compute this, and let's just, I'm gonna come back and call it this. So step 1 is use the ratio test, find this. It's gonna turn out to be 1 over the r, but let's see that instead of me just telling you that. So what is that gonna look like? And I literally write this out. So what is u sub n? It's a n plus 1 times x minus c to the n plus 1. That's that whole term. Does that make sense, Jose, how I'm grabbing that? This u sub n, that thing we just talked about, that's what I'm writing here. Okay, cool. Times 1 over a sub n times x minus c to the n, absolute value. So take a minute. Make sure that every step of the way this is working for you because you're going to do this. Pen's already dead. You scared? Are you good? Are you still processing?
I'm processing.
Okay. And we'll do some examples, and it'll come. So to kind of make sure you're roughly following, and then when we do it with actual examples, it'll probably make a lot more sense.
Okay.
But then we'll have this process recorded, and so look some stuff that is going to be good happening here. First off, we're going to have a n plus 1 times 1 over a sub n, this stuff here. But what's going to happen when I take this divided by this? So in other words, x minus c over n plus 1 divided by x minus c in the n. What algebra can be done here?
We move the denominator to the side.
I'm thinking of something a little similar. Cancel.
Oh,
What cancels? Is that what you were going to go
I
for?
was actually thinking subtract the powers.
Subtract the powers, yeah. So I thought maybe you were saying something like that. Yeah, that's it. So I subtract the powers, and that's just actually what? just x minus c did first. Yeah. Right, n plus 1 minus n, 1. That hurt your back?
No, I just
Okay,
popped my
okay,
head.
okay. So then here I'm just left with x minus c to the first power, because those two cancel. So now check this out. This is equal to, this part doesn't even have an n in here, so there's no n. It doesn't even matter for the limit. So this is just this times this, and I'm gonna pull this part out and just have x minus c right there. Because there's no n on that. It doesn't, we don't have to worry about it being a limit. It's like a constant, and it's gonna change depending on what x is. So this is just some number, depending on x. So what is the ratio test? What do you need this limit to be less than for convergence?
1.
Yeah, less than 1. So it must be less than 1 for convergence. Exactly. So let's see what that means. That means I've got this limit here. So this means, I'm going to put a little right arrow, so this follows from that limit as n goes to infinity of a sub n plus 1. Actually, sorry, let's call this r. So this limit is r. We called it L in the past, but L's here L is the whole thing. We're just going to call that r. In fact, we're going to call it r to the negative 1, because I'm going to freaking move it to the right side. So this is equal to r inverse, just using that notation. And again, this is 1 over r. I'm calling it that for a very good reason. So this tells us this, that r inverse times this thing must be less than 1. And now I'm going to multiply both sides by r. So x minus c has to be less than r. And what was r? Where r is 1 over that quantity. So it's going to be this limit, as n goes to infinity, of the coefficient stuff. Let's put a 1 over there. That's it. Yes, sir.
I didn't understand the r to the minus 1 part.
I'm calling it that because I could have said that this was r inverse over here, but I wanted a pretty r there, so I just called it that. Let's call it.
But she's different than the other r.
What do you mean? Sorry.
Like the r to the minus 1. It's different than the r.
No, it's the same. So if this number turns out to be, it's just notation, honestly. I could have called this r right here,
Okay.
and then this would have been r inverse over here when I divide both sides by r. But I kind of wanted an r over here
Okay.
because it's the radius of convergence. Is that, yeah?
I just want to know if they are the same.
They are the same, yes, sir.
Okay.
Yes, yeah, absolutely, they are. But this one is 1 over this one. That's the only difference. So this thing here is 1 over this.
Okay.
Yeah, cool. And I swear, Athman, it'll make more sense when we see a solid example. So step 1 is find this limit, but i.e. it's really this, i.e. find this r equals 1 over the limit as n goes to infinity of the coefficients. We don't even think about the actual x part. We're just going to grab the numbers or the formulas for the numbers off the front, find this, this is our radius of convergence. Let's look at a special case, a couple special cases. If this limit here, if limit as n goes to infinity, and this is what you're gonna crank out, you're just gonna take the reciprocal of it, equals 0, then I've got 1 divided by 0, we just say r is infinity. And we can move as far away from the center as we want. This means all numbers work. The whole real line. If that limit is infinity, what do you think r is? Let me write this up. If this equals infinity, what do you think 1 over this is? 0, exactly. That means you can't move away. It doesn't converge for anything except the center. Then the IOC that only converges at the center. Cool. Well, I'm erasing this kind of, let that process, but again, this will come together more when I do an example for you. I want to lay the whole process out so that when you go back and watch this after working some examples, you're like, oh, that's what that was. And so right now you might be like, feeling a little foggy. It's okay. That sounds right. So that's step 1. Step 2 is rewrite. So rewrite x minus c less than r. So this first step is finding r. It's just a limit. Rewrite this as x minus c is less than r, and it's greater than minus r. That's just, we've done this in the past where you've got this inequality with an absolute value. It just means this. In other words, x minus c is between r and minus r. That's really all it's saying. This quantity is no more than r units away from 0. But then we're going to rewrite this, bless you. Thank you. This means, and so you could actually even just go right to this, add c to everything, that x is between the center plus the radius and the center minus the radius. This is our interval of convergence. Okay. Interval of convergence. I'm flying. We're flying. It's going to be all right. I'm going to make a couple support lectures for you as well, I promise.
Support notes on the exam.
Support notes, yeah. And I'll make a video where I work through the practice final, the multiple versions that I'm going to give you. The final is going to be just like those. I promise it's going to be okay. On Monday, on Friday I'm in from noon to our class. So right before class, we're going to meet. I'll be here till 3:30 if you want. And on Monday, I'll be in from 10 to 2 in my office. And then Tuesday, I'm available via Zoom. I hope we don't have too many issues on Wednesday, but we'll talk about it as we approach. So this interval of convergence, you want to draw this out, it just helps. Here's the center. Here's c plus r. Here's c minus r. And all these values in here, the series converges for. The series converges absolutely for x in here. That's what we just found. Let me give you a quick example so you can see this. What's going on? Everything okay? You all right? Okay. Oh, you like taking your nice notes there?
Well, not the, you just didn't hide everything.
Oh, okay. And the recording will be available if you should be one. Okay, so example. Find the IOC of.
You said it's a two-step process.
This is step 2.
You-
Yeah, it is a step 2 process,
Is
yes.
there's a third step or no?
No, 2-step. That's it. There's a third step I haven't talked about yet.
Alright.
two steps, but counts for like 8.
There's two steps. In a way, there's actually in a way, Jose, let me just summarize really quickly. Step one is find this. R equals 1 over the limit n goes to infinity of those coefficients. That's step one.
I did feel it was slightly dramatic when you said step one.
I agreed. Fair enough. This is step one. Find this. I kind of wanted to give you all the deets so that you knew why I was doing this, but that's step one. Find that shit. Step two is write this. Take that number and add it to the center. That's all. So let's take a look here at a series. I'm going to say I've got x minus 1 to the n over 2 to the n. N equals 0 to infinity. Find the interval of convergence. Got to find all the x values that work here. So the first thing I'm going to do is figure out what the coefficients are. And you might want to rewrite it. It's 1 over 2 to the n times x minus 1 to the n. Let me stop and tell me if that looks okay. All I did was break the fraction into the 1 over 2 to the n. Because I want to see this part. What is my center? So the center is the number I'm subtracting off. 1. Center is 1. Notice that if I replace x with 1, this series doesn't, it's just a bunch of zeros added up.
You said X or center?
Oh, I said center first. The center is 1. If I replace this x with 1, then I just get 0
Yeah.
there. Does that make sense? So the center is the thing that makes this stuff 0. The x value that makes this part dead. So, okay, so what is a sub n here? It's this part. It's that number in front. It's 1 over 2 to the n. Just grab it. So what is a n plus 1?
It's x minus 1.
No x's, no x's.
Oh,
So just this formula, take this formula. What do I get when I replace n?
oh,
n
1 over 2 plus 1.
Yeah.
There we go. Awesome. Yeah, you're thinking too hard, too much. And I can see why. But this ends up being a little simpler than we maybe feel it might be. So then I'm going to compute r equals 1 over the limit. And you might want to just do a little scratch work on this limit. I'm putting it here to keep everything as compact as possible after what happened over there. So this, I'm going to write the formula out again. So this is 1 over 2 to the n plus 1. What's this?
1 over.
1 over that.
1 over
And what is 1 over that?
2 to the n.
2 to the n. Beautiful. Let me stop. What is that limit? Do the canceling first. No. Let's slow down. Let's do the canceling together. What's left after I do the canceling here?
So 1 over 2?
1 over 2. Check that out. Make sure you see that. This is 2 to the n over 2 to the n plus 1. Just left with a 2. You got 1 extra 2 at the bottom. Whatever's on top, it's times an extra 2 at the bottom. So that's just a half. What's 1 over a half? I think I heard 2. Yeah, I heard 2. 2. That's my radius of convergence. See, it's not that bad. Like getting here was worse. The hike was worse than the view's great.
So in this case, it doesn't converge. Diverge.
We're not.
Wait, so what's your question?
Does it converge divergence?
Well, I'm going to take this and I'm going to use this to figure out where it converges.
Also, we can say if it converges or diverges here.
Well, it will, so let's talk. So this thing definitely converges when x equals 1. Let's write this series out. I mean, what does this look like? When n equals 0, I just get a 1, right? Because it's 0 power. Plus, then when n equals 1, I get x minus 1 over 2, x minus 1 squared over 2 squared, x minus 1 cubed over 2 cubed, blah, blah, blah. So notice that when x is 1, it does converge. It's just 1 plus 0 plus 0. So I know it converges at the center. I'm trying to figure out how far away from the center I can move for x. What values of x can I put in there that it does converge for? And that's what this r tells me. I can move 2 units away from the center in either direction and I'm good to go.
Because earlier we said that it must be like less than 1.
Yes, that was how I derived this formula. So what you would do here is you would, yeah.
I'm just confused, I'm sorry.
It's okay, it's okay. Focus on this. If you understand this process, you don't need that.
Okay. Because I'm stuck with it should be like less than 1.
Yes, that was, but then I did some algebra.
I see what is concerned. See when you're finding the limit of the equation and it's greater than 1 or less than 1, then it converges or diverges. So when you see the answer.
Yes, we got, so I'll just show you really quick. We needed this to be less than 1.
Oh, okay.
And for that to be less, and then this was x minus c here. And so I divided both sides by that. And so x minus c has to be less than 1 over this thing.
Oh, okay.
And that's where I'm getting that from.
Okay, gotcha.
Does that help?
Yeah.
Okay, cool.
In the center, you just plugged in 1 for x.
Yes, sir.
To get 0.
Absolutely. Yeah. So the center is the thing that kills off this. Just remember that. Okay, so r is 2. R equals 2. The center is 1, so I'm going to move 2 units this way, and I get what? 3. And then when I move 2 units this way, what do I get? Negative 1, beautiful. See, there's some confidence building computations for us. We got it, good work. Well done, my friend.
So I have a question about this over here.
Yes?
So are you saying that on the left side, it only converges absolutely, and not on the right side?
It converges in this whole thing.
Okay.
Whatever that radius is, that far I can move to the right. If I pick an x there, it works. Pick an x here, it works. Pick an x out here, doesn't work. Yeah, does that help?
Yeah.
Okay. We good?
Yeah.
Okay. This is finding the interval of convergence. So the stuff at the beginning was to get us here. This is what I need you to know. This, right here, grabbing that stuff, finding that r, is pretty rough after a 20-hour drive. You with me?
Yeah.
Okay, cool. You're actually more awake now after that 20-hour drive than you generally are. This is great. So my interval of convergence is this. So the interval of convergence, I write this out as -1, x has to be between -1 and 3. Step 3. Step 3. Step 3 is not too hard. Test the endpoints of the IOC.
Right, yeah, okay, right.
Test the endpoints of the interval of convergence. That means I'm going to have to test, because sometimes it actually it won't converge outside of this, but it might converge on the edge of this. So it might converge when x equals -1, and it might converge when x equals 3, but I got to plug that shit in and look at it. So, plug the endpoints, and there's only 2 endpoints, to worry about. Plug the endpoints into the series and use your series skills. Is it a P series? Is it an alternating series? It'll be one of those two, I promise you. And does that converge? So, I'm going to test the left one first, just because it sounds left to right, because I'm working with that bias. So let x equal 1, and plug that into this star, right here. Plug into the series. So your series, you have to look at the series you have. But what does that thing look like when I replace x with -1? Like that. So I just replaced the x with the number -1. Do we see any simplification that can happen here? Yeah, what is it, PK? -2, yeah, exactly. So I got -2 to the n over 2 to the n. It is alternating, absolutely. It is -1, yeah, that's it, Yusuke, that's it, perfect. So notice that this is just this. Because you can bring that n to both, you can rewrite this as -2 over 2. Isn't that what you were doing, I think?
Yeah.
And so that's just this. Does this series converge?
No.
Yes. Because it's between, oh,
It's
wait,
either
it's between -1 and 3 though.
One.
Look at this.
That's,
This guy. This is 1 minus 1 plus 1 minus 1 plus 1 minus 1. What test tells us this can't converge? Alternating series, definitely, because the terms have to die out. The terms are not dying out. Alexander, this series is just adding 1 and -1, 1 and -1, so it can't calm down ever. We need these, so the divergence test tells us, or the alternating series test, which has the divergence test built in. So this diverges. Let's do x equals 3. This is why you're going to get a lot of practice between now and next Wednesday. Because we got to pull this stuff together. So I'm going to plug x equals 3 in. What does the series look like when I plug in x equals 3? 3 minus 1 to the n over 2 to the n. What is that? Take a minute and just think about that.
one to them.
It's just 1 to the n. Yeah. So this is sum. Wow. That's bad. Sum. Does that converge? It does not.
No.
Alexander, does the series converge?
It does not.
How come?
Because it goes to 1, it's 1, doesn't go to 0.
It doesn't go, that's it. There you go. So it diverges. It's just a bunch of 1s added up forever. The shit just piles up forever. Yeah, exactly. So it diverges here. So we're done. If one of those had converged, say it had converged at 3, I would have included 3. If not, like we have, this is it. So we don't include the endpoints. This is it. This is the interval of convergence. Those are the only x values this converges for.
We don't need to test what's inside to see if it actually converges.
No, because we did that with this. This process tests that for us. That was the whole setting it less than 1.
Okay.
Because we had an inequality, so it gives us everything in between.
Oh, I see. Okay.
Yeah?
Yeah.
Okay, cool. All right, that's the first thing I want to tell you.
Oh.
Done. Oh, yeah. Oh, no, we're not done. Take a shot of whatever you got. Caffeine. Next thing I want to tell you is why do we care about any of this? You may be wondering, why did I take count 2? Yeah. My God, what did I do? So, I want to talk about Maclaurin and Taylor series. And this is beautiful. So Maclaurin, Taylor, I'll say Taylor, and Maclaurin series. If you're a scientist, this is what you care about from this class. It only took a semester, and we're in the last half hour of anything I'll tell you. So suppose I've got some function, f of x, and I can write it like this. I'm going to treat this thing like a function. So in other words, treat this series, this infinite series, this infinite polynomial as a function. And we see, you can see that as x changes, that value is going to change over there. We know how to figure out what x's are good. We just showed that process. So we can figure out what x's are good for this. So assume we got a good x. Assume we have an x in the interval of convergence. I'm going to start doing calculus now. I'm going to differentiate that thing. And differentiating this is pretty sweet because this is just a polynomial. That's just power rule shit over there. So let's take derivatives. We're almost there. Like honestly, the payoff is pretty fast here. Take derivatives. So f prime of x, if this thing is a function, what's the derivative of that with respect to x?
0.
0. Beautiful. What's the derivative of this with that one?
0.
X.
A1.
Oh, just A1, right?
Just A1, so yes, bless you. Because think about this, this is A1 times x minus A1 times c. That's a constant. Goes to 0, and that's just A1.
So the number is x or a1?
I'm differentiating with respect to x.
Okay.
Does that make sense?
Yeah.
Yeah, I just get that. Just think like 3x, you get 3.
Yeah, I got you.
Okay, cool. And then the next term, I'll show you a little speedier than this.
Well, I'm just like.
The 2 comes out in front, power rule first, and then the derivative of the inside, I'm using the chain rule as 1, so that's the derivative of the next term. Let's write out this next one so you can see it. A3 times x minus c cubed. What is the derivative of that term? Take a minute.
3A3.
3 comes out in front.
Yeah. X minus C. Power 2.
Beautiful. Yeah, we see the rhythm? What's the next term without me writing it out? Look at the rhythm.
4A, 4, parentheses, x minus c cubed.
Beautiful. Beautiful. Okay, and then so on and so forth, right? What happens when I plug in the derivative? Excuse me, the center. When I let x be c, what am I left with?
0 plus A1.
0 plus A1. Just
A1, yeah? Okay. Off mine.
I got you.
You got it? You good? Okay. Everybody good? All right, fuck yeah. All right, well, let's do it again. So take this series and differentiate it. So I'm going to do d dx again. I'm just going to note this. We already know that f at the center is just a knot, so let's record that. Take the derivative again, so now I'm going to do f double prime of x equals, let's do the derivative of this. What's that go to?
0.
0. What's this go to?
2A2.
2a2, beautiful. What does this go to? 3 times what happens when I differentiate? The 2 comes out front.
Oh, yeah.
I'm going to write it, instead of saying 6, I'm going to write it like this, because we're going to see something pretty.
Okay. And then A3.
A3.
And then, let's see, then we had, oh, sorry, so let's, A3, thank you, yes, I see what you're saying, x minus c to the first,
power.
plus what?
4 times 3. A4. X minus 6 squared.
Beautiful. Yeah. Let me stop. What is f double prime at c?
2A2.
That's it. 2 more. 2 more. Like seriously, this is like, we're on the cusp of a secret of the universe. I swear to God. This is on the cusp of one of the greatest things you'll ever learn in math.
Wait, are we taking, you saying we're taking 2 more derivatives? of
Yes,
that?
sir.
Is it follow that pattern?
It sure does. Let's see if we can grok it just real quick, so. What's that?
Don't wanna take more of it.
Oh, come on, now you're doing it.
I know.
Now you're gonna do it with me after that. Alexander, what's the derivative of that? Yeah, so 0, I'm not gonna write that. What's the derivative of that?
As 3 times 2 terms,
And I'll put a times 1, right, but then, what's left, just the A3?
there's the A3.
Yeah.
And then 4 times 3, 8, 4,
And what comes down?
oh, times 2, sorry.
Yep.
And then x minus c the first.
Beautiful. And then what would be the next
You
one?
know,
4
do you
times
put
3
the
times
D4?
2 times 1.
Oh, thank you, yes, the A4, yes, thank you.
Oh, yeah. Okay.
Yes, and then what's next?
4 times 3 times 2 times 1.
5 times 4, oh, sorry, yes. No, there would have been 5, right, because we don't even have him up here, right? But the rhythm, this is the A4 coefficient.
Oh, yeah, we're bringing it up, okay, yeah, so we
Yeah.
start at 5, and then goes to 4, and then to 3, and 2, and then 1.
And
then
x minus c.
to the second power.
Cool,
Yeah.
see, that wasn't so bad, now let's do one more.
Yeah.
And then let's actually, let's do this guy, we evaluate him at the center. What happens? What am I left with?
Wait, what do you mean? Oh,
683.
6A3 or
3 times 2 times 1, A3.
A3, yeah.
Plus 4 times.
No.
Oh, are you just wanting to do?
X equals C, dead,
Oh, at C.
dead, boom.
Right.
Everybody with me?
Yeah.
This guy, you with me?
For some reason.
Okay, I know you're tired. I know you're tired, my friend. We've got one more. I won't make you do this, Alexander. I lied, you're gonna do it with me. Yeah. What's the derivative of that?
Nothing.
Yes, what's the derivative of that?
Just the 4 times 3 times 2, a to the 4.
Yeah, and I'm gonna put a 1 in there, but A4, yep. And then,
5 times 4 times 3 times 2 times 1, x minus c.
And I forgot.
A3,
A5.
A5, yeah, A5, x minus c the first.
beautiful. And then, so on and so forth. Okay, that's enough.
It's like factorials.
Yes! Is that what were you gonna say, Jose? Yes.
No, I'm not gonna say that.
Were you gonna ask a question though?
Yes.
Yes, sir.
So why is A5 5 times 4 times 3 times 2 times 1?
Because if we had kept going, the next thing here would have been 5x minus c to the 4th, just looking at this rhythm.
Right.
And every time I take a derivative, the exponent comes down and also diminishes.
Yeah.
So after doing this 4 more times, for next time I'm gonna get 5 times 4, a5x minus c cubed. Then the next time that 3 is gonna come down front. Get that. And then I do it again. So that was, this one is there.
Oh,
And
so
then, yes,
the reason I was getting confused is because up there it says 5 times 4 times 3 times 2 times 1, A5x minus c squared.
oh. Yeah, here for this one. This was this level, oh, yeah, sorry, thank you. You got it, yeah, you're really on it, man.
Yeah, and then
That 2 hadn't come down yet, you're
right,
so right.
and then this one would be
Yes, sir.
okay, cool. That's why I was like,
Damn, bro, that's great. That's awesome. So, when I evaluate this at C, so this is 4 factorial, right? This is 3 factorial, this is 2 factorial if we want a rhythm, and then there's like a 1 factorial, which is just 1, and there's a secret 0 factorial, which is just defined to be 0 anyway. I have 1 defined to be 1 anyway. So what is this in factorial notation?
4 explanation a
To the 4th.
for the 4th, yeah.
Okay, so without doing derivatives, what's that?
5, same thing with 5s.
What's this?
The 6s.
Beautiful. Okay, so there's something beautiful happening here, but there's something super profound. The coefficients in this series, we now have the formulas for. A0 was just F at the center. A1 was f prime at the center over 1 factorial if I want. This was f double prime at the center. Do you see where I'm getting that from? I'm solving for A2 here.
Yeah, I do. And then that's 2 factorial?
And over 2 factorial. What's this?
3f prime over 3 factorial, triple prime,
And then, yeah,
quad prime,
yeah.
prime, hexaprime,
Do we see?
heptaprime.
So let's write this out. This is Taylor's theorem. And it shows you that every function is really a secret, hidden, infinite polynomial underneath. So Taylor's theorem says this. I've got a function f of x. I can write it as f at the center. I pick the center. So we choose the center, C. I'll tell you what that is. You don't have to imagine what it might be. I'll always give you a center. And then you plug that into the function, you get that term. And then we don't need to put the 1 factorial here. Then f double prime at c over 2 factorial x minus c squared plus f triple prime at c over 3 factorial x minus c cubed. I'm going to do one more. 4th derivative at c over 4 factorial x minus c to the 4th forevermore. So what I like to think of this as is a prism. Think of light prism, right? You pass through white light into a prism. So you got a prism. You pass through a beam of white light. What comes out are the components of the white light. How much Roy G. Biv is in there? How much red, orange, yellow, green, blue, indigo, violet? And this is how astronomers can tell what the atmosphere of a planet is made out of, right? They take it and they do a spectroscopy and they see what bands are missing from that spectrum, and they compare that with the elements and what their spectral profile is. So this is the spectral profile of a function in math. How much first degree stuff is in there? How much quadratic? How much cubic? How much chordic? So let's do one. And let's do the most beautiful one of all. So the only difference, this is arbitrary center C. This just means center equals 0. That's all. And then I'll give you a quick way to see what the interval of convergence is. It's actually much simpler than the other stuff. So example, find the Maclaurin series for f of x equals e to the x. All right. Hey man, we got to take some derivatives. Could you get a better gift for derivatives? So step 1 is find a bunch of derivatives. And I would record these, keep track. So f of x is e to the x. F prime of x is what? Oh, hell yeah, we learned some shit. Next. Right, we got this. They're all e to the x, right? So, cool. The center is 0 because I used that word. That means use c equals 0. When you see Maclaurin, it means Taylor series with center 0. That's all. So step 1 is find a bunch of derivatives. Step 2 is plug the center into the derivatives. Am I going to be on social media or something with that? Just her picture got taken over there.
Oh,
Was that you?
no.
No, it was
I think you might be hearing things.
Well, I didn't hear light. I hope not. I'm not having synesthesia.
Yeah.
Hopefully. My God, it's just tea.
Let's see, is that something?
It might have had something in it. It's the end of the semester. All right, so plug center into the derivative. So f of 0 is what? What's e to 0? 1. What's f prime of 0?
Wow, every time I didn't say that.
Isn't that sweet?
So one.
It's so 1.
So one.
Are we good on this? Cool, now plug it into the formula. Let's just do that up here. So, this is gonna be this, so C equals 0. That's just 0, 0, 0. See, what's cool about these is they're just powers of x. When we right? Because x minus 0 is just x. Make sure you see what I'm saying. I'm gonna write this to the right. Oh yeah, we've done it. We've honestly succeeded in getting where I wanted to get, amazingly. You're all our troopers, I'm proud of you all. This was a hell of a hike today. So f at 0 is 1. F prime at 0 is 1 times x. Okay, x minus 0 is x.
I agree.
Yeah. What's the next one? What's this?
X minus 0 squared.
What's that? What's f double prime of 0?
So,
Just 1 over 2 factorial. I gotta include these.
Okay, so it's just 1 over all.
Yeah.
See, I got it.
What's the next term? What's the rhythm?
1 over 3 business, and then x to the 3
Yeah,
business, yeah. The explanation point business.
exactly. This is E. This is the Maclaurin series for E. It's just absolutely beautiful. I would write this down and have this on my note sheet just in case. Now the exam's open note, but for the love of God, organize your thoughts on a page anyway, right? Don't just be flipping through. Where was that? Put this shit in one spot. A couple of pages worth. Okay, so that's the Maclaurin series for E. Let's, what? Well, okay, slow down. Yeah. There we go. Let's see something kind of cool here. So this is supposed to be e to the x. E to the x. Now, if you wanted to have a quick formula for e to the x, you could just grab a part of this and get an approximation. So, for example, e to the x is approximately 1. Not very far away from the center. The center is 0, and we know that e to the x at 0 is 1. So you can't move very far away. The further out here you go, the more accurate this will be away from the center. It's also approximately that. Hey, guess what? The tangent line at 0 is x plus 1. If I want to make it a little better, that's a better approximation.
With a factorial.
With factorial, yeah, I just 2 factorials 2, right? Here's a slightly better one. So if I was doing some quick computations near the centers for small x, this is going to be pretty damn accurate. We don't have time right now. I'll do a video on it. But like, if I wanted e to the 0.1, this formula, well, hell, we can do this. So that's approximately 1 plus a 10th plus 1/100th over 2, so 1/5 thousandths. And that is approximately 1 point, oh wait. Yeah, because 0.1 squared is 0.01, okay. So approximately that. Could somebody just do a calculator version, get e to the 0.1 for me? Isn't that cool? This is freaking amazing.
0.105.
Oh, no kidding.
Yeah.
What? Shit, look at that. Power. Now, I'm going to give you a couple others, and I actually, I'm going to give you a couple of these on practice exams. So let me show you, because, oh God, you don't have to know what's about to happen, but you have to see what's about to happen. You cannot leave this class without what's about to happen. I'm going to give you a couple of other famous Maclaurin series. So, important, I wouldn't say famous, important Maclaurin series. So first off, we've got our good old friend e to the x. Another great one is cosine. Now, the radius of convergence on these is infinite. So for all these, r is infinity, the ones I'm gonna put up here. No matter what x you get, they're good. Cosine is really interesting. It's 1 minus a half x, 2 factorial, 1 over 4 factorial x to the 4th, it's alternating. Notice how it's kind of the even powers from e with an alternation tossed in. To find the series for sine, I could just differentiate this and differentiate that and make sure I take care of the minuses, but I'll give you sine. Sine is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, we'll do one more, 1 over 7 factorial x to the 7th plus minus ever more. It's like the odd powers from e with alternation. Hey, just a quick check on something. What should the derivative of sine be?
Negative cosine.
Positive cosine. Positive cosine.
Right.
So the derivative of this is cosine. Well, let's do the derivative just really quick on this right side. What's the derivative of x? What's the derivative of this term?
2 over 3,
So 3 over 3 factorial, right? The 3 comes out front.
Yeah.
What's 3 over 3 factorial simplified to?
1 over 2.
That 5 comes out front, cancels with the 5 in that 5 factorial.
Over 4 factorial.
Yeah. Serious much? Oh, yeah, okay, fine, all right, there we go. We're seeing some things. We're seeing some really awesome things. So, now what I gotta tell you is fucking crazy. And you do not need to know this at all, but you need to know it for life and happiness and maybe a cool tattoo. What's this number? Square root of negative 1. What? Oh, yeah, that's I. Imaginary number. What's I squared? Negative 1. What's I cubed? It's negative 1 cubed, so it's negative I. Right? It's I squared times I. And I squared is negative 1.
Imaginary numbers, right? Yeah.
Yeah. What's I to the 4th? It's I squared times I squared. Minus 1 times minus 1? 1. What's I to the 5th? Yeah, square, it's back to I again.
Right, yeah.
Yeah. So it's I again. Look, check out, and so I, let's just say I to the 1st is just I. What's I to the 0? Just 1, yeah. So look, there's a rhythm here, cycling. 1, I, minus 1, minus I, 1, I, minus 1, minus I. Something like that. So I probably said it wrong. I said it as something fucked up. But do you see the cycling that's happening every 4th power? We get back to where we started. There is something cyclic happening here. Let's think about it. All right, so what I'm going to do is I'm going to take this series, and I'm going to replace x with ix. So I'm just going to take, so this thing here is really a little box. If you wanted e to the 2x, you could just replace all of these x's with 2x. In other words, this is a formula I can do whatever I want with. You want e cubed? 1 plus 3 plus 3 squared over that, blah, blah, blah. I'm going to put ix in there. So we get 1 plus ix plus, let's write it out real carefully here, ix squared plus 1 over 3 factorial ix cubed, 1 over 4 factorial ix to the 4th. And this, honestly, this is the only reason I even teach this class, is to show you this. And I just can't be complete if we hadn't, I would have been so sad. Does this make sense where I'm getting that formula from?
Yeah.
Taking the E series and replacing the X with IX.
Which is the center, right? Like the McLaren or.
Yeah, the Maclaurin series, yeah, this guy, yes, the
That
Maclaurin
was
series,
the
yes,
Center.
absolutely, the center 0. Yeah. But I'm just taking that rhythm right there, Alexander, that series expansion and putting an IX in where there was an X.
Does that make it like no longer a McLaren series?
It's still a Maclaurin series, it's just a complex imaginary value one.
Okay.
That's a really good question. It still is. You can actually do these series in the complex plane, but you get bless you get a disk of convergence as opposed to an interval.
Oh, that's interesting.
It is interesting, yeah. It's take complex analysis next time it's offered. You'll have a good time. Now watch this. We're going to take that powers of I stuff. So this is 1 plus IX plus 1 over 2 factorial I squared. What's that?
Negative.
-1. And then I have X squared. 1 over 3 factorial. What's I cubed? Negative I. So I'm going to put negative I there. X cubed. 1 over 4 factorial. What's I to the 4th? 1. What's I to the 5th? 1. I. Let's write out a couple more. Then the next one would be I to the 6th. What would I to the 6th be?
1 over 6.
Negative, something negative.
No, slow down. So let's just this part, just this. Yeah, you're right. You're doing the whole term. I squared, I squared, I squared,
-1.
-1. So it's going to be minus, and it's real. Notice how every other term is a real thing, and every other term has an I in it. So this becomes 1 over 6, negative 1 over 6 factorial x to the 6th. And now I'm on this rhythm here. The next one is minus 1 over 7 factorial. I'll have an I. So I'm kind of pulling that I, that minus, putting it up front, leaving that I there. X to the 7th. The next one will be just 1 over 8 factorial x to the 8th. And then this just repeats again. 1 over 9 factorial I, x to the 9th, minus 1 over 10 factorial x to the 10th. Blah, 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 blah. Whew. Now what I'm going to do is let the things that have an I coalesce together and the things that don't have an I coalesce together. So there's stuff here that's real and stuff that's imaginary. So let's put the real stuff together. Help me write the real stuff. So 1, what's the next real term with no I on it? Yeah. What's the next real term? Beautiful. Uh-huh. Minus 1 over 6.
Exclamation point and the eyes being right next to each other.
And then this
Like,
stuff,
why are we-
now let's do the I stuff. I've got an I times x minus 1 over 3 factorial x cubed. Next I term is plus 1 over 5 factorial x to the 5th minus 1 over, is this looking familiar? What's this the series expansion for? Cosine.
Yeah, we just did that.
What's this the series expansion for?
Oh, sign, right here, okay, yeah, it's right there.
So, e raised to an imaginary power can be computed like that.
Ooh, that's cool.
Oh yeah. So this is called Euler's identity. Euler is, to mathematicians, a demigod. Just a god, a math god in human form. Euler was doing shit when he fell out of the womb and started just like doing math on the birthing table. Euler's identity just flowed from it. But what I want to show you is a very special case. Let's let x equal pi. Do you have a picture of Euler on the birthing table? No? Okay. So this is cosine of pi plus I sine of pi. What's cosine of pi? Come on, picture the graph.
It's 0.
One more guess. Oh Lord.
Oh, minus 1.
There, thank God. Oh my God.
Think
Yes.
about anything at all.
Jesus Christ. What is sine of pi? 0. We only had one more guess. 0. So e to the I pi equals -1. And so when I move those to the left side, all of the it's e to the I pi plus 1 equals 0. This relationship puts the 5 most important numbers that we know in relation to each other. I, pi, e, 0, and 1 all relate together in this beautiful way. Now that's the tattoo.
That's cool.
Right here.
That's it. Right there. Actually, I've known at least 3 people who've gotten this tattooed after.
Oh, really?
Yeah.
I think I'm about to get sine and cosine graphs, just so I don't ever mess up.
Yeah, that's actually, let's get those first. Yeah.
One here, the other one here.
Yeah, right? Your sine and cosine graphs on the back of my hand.
Really,
Back of my hands.
really quick, cool version of this. What is, so what if I replace, oh wait, let me see, what is the one I want to do? E to the x. Oh, right, okay. What x value would kill off, this will be fun. Do you have that tattoo yet? Because you're gonna need it. What x value gives me cosine of 0 but a sine of 1? Where is cosine 0 and sine 1? The first location to the left.
It's cosine
Pi over
is,
Yes. God, yes. So e, so e to the I times pi over 2 is cosine of pi over 2 plus I sine of pi over 2. That's 0, as we all agree. That's 1. So e to the I pi over 2 equals 1. So first off, e to an imaginary power is a real number. That's crazy. But the crazier part, oh wait, sorry, this is I, 1 times I. That's 1 times I. That's, ooh, it's still imaginary. So here's what I want to show you and we're done. This is it. This is amazing, but this, I kind of like this one a little better because what I want to do is think about what I to the ith power is. So I to the ith power, well first off, we know that we can write I as e to the I times pi over 2. So this guy is e to the pi over 2i raised to the ith power. What do you do with exponents when you raise the power from? What? Multiply them. Yeah, that's what we all said. Multiply them. So e to the pi over 2 times I squared. What's I squared? Minus 1. So I to the ith power is a real number. It's this real number. That's it. Thanks, friends.
Thank you.
That thank you sounded like a question.
Thank you.
Thank you.
You just said you put a green cap on a black marker.
Yeah, I did. Everything's
has
out the
two
window
caps on
now.
And there's no, and
It's
there's
double.
no cap on the green marker.
Yeah,
for the
fuck it. I'm done. All right, so Friday, work day.
Okay.
I'll see you on Wednesday at the final.
Exactly.
It's the last lecture, no one cares.
What's that?
It's the last lecture, no one cares.
The markers.
Yeah, no one cares, exactly.
Because it's the last lecture.
Come again? 1:15 in this room next Wednesday. 1:15. I will be in my office Friday, noon to 2, and I'll be here, normal meeting time. Monday, I'm in from 10 to 2. Keep an eye on world class. Stuff will be coming for you.
One of them just did
What's that?
practice exam.
Practice exams. And maybe some videos that walk through some things. All right, thanks guys. It's been fun. I appreciate you all. Well done. Yeah, go have a drink.